Ok.
Andrea mi ha chiesto in che lingua farò la mia presentazione. Allora,
Forse è spento.
sì, Andrea mi ha chiesto in che lingua farò la presentazione. Io la farò in inglese sicuramente, però per reciprocità con status vorrei dirvi sa se faristo Kyrie proedre, Kyrie che Kyrie, in megalitimi, iemena nodo saftiti nomelia, a questo bellissimo congresso di ReLUIS, che era, thank you Andrea, ladies and gentlemen, it is for me a great honor and a great pleasure to have been invited to contribute to this meeting, very important meeting of the ReLUIS community. So before I start, I would like to narrow down the scope of my presentation a little bit, because I will talk about the seismic behavior of yielding retaining structures only, trying to move from some fundamentals very quickly towards some indications for their performance-based design. Now, yielding or ductile retaining structures may include gravity and semi-gravity retaining walls, but also embedded, flexible walls, whether cantilevered or propped or anchored. And the common feature of all these structures is that they're not kinematically constrained, so they can experience large displacements during an earthquake without failing. That is to say that the instantaneous mobilization of the strength during the earthquake does not correspond to collapse. Now, because of reasons of time, in this presentation I will just deal with one type of yielding retaining structure, that is tied back anchored steel sheet pile walls, ASSP walls. Now, mainly because of the ease of installations, these walls find a lot of applications in the formation of seafront structures. And in fact, because of the increased vessel size and the increased required for draft, often these are used in a combined reclamation plus further dredging, and very often in front of existing quay walls, such as, for instance, in the case of the Cuba port expansion. Also, an overlap between the shipping routes density and the seismic areas of the world indicate that if we want to use this type of structures for seafront structures, the question of their seismic design is absolutely vital. So we cannot ignore the seismic design of the structures. And it must be said, it is fair to say, that there are many, many reported cases of damage to seafront structures that are very often associated with excessive displacements and sometimes failures, but very often these failures are not brittle failures, they are rather excessive displacements that have compromised the serviceability of the port infrastructure. Now, what sort of tools do we have to design this type of structures? In the conventional seismic design, the simplest approach is the pseudostatic approach. In this case, what we assume is that the soil around the structure is in limit conditions, either active or passive states, and we represent the seismic actions using pseudostatic equivalent forces that are proportional to the masses through some seismic coefficient, horizontal and vertical seismic coefficient, which is constant in time and space. So we reduce the effect of the earthquake to a system of static forces. And very often the pseudostatic, the equivalent seismic coefficient is proportional to the peak ground acceleration, to the maximum acceleration expected at the sites. Of course, this is the most basic approach. As an alternative, we might think, okay, let's carry out some advanced numerical analysis, which could be done with finite element or finite differences, typically carried out in the time domain, so they're fully coupled analysis, with advanced constitutive models to represent the nonlinear and hysteretic behavior of the soil. However, these analyses are very complex. Of course, they can be used to directly check whether displacements, rotations, and movement of the structure are acceptable under the design earthquake, but they can be very, very demanding from the computational point of view. And it's not just a matter of computational point of view, it's a matter of general expertise of the person that needs to carry out the analysis, parameter identification, boundary conditions, and so on. So are these two approaches feasible for the type of structure I want to talk about, that is anchored steel sheet piles? To answer to this question, I have plotted in this graph typical steel sheet pile solutions on the y-axis versus peak ground acceleration. And I have identified some areas from the most economic typical Z sections to the much more expensive and non-economic combined systems where you combine several steel profiles together to have a very resisting wall. Now, if we use the pseudostatic approach, the actions increase very rapidly with the peak ground acceleration, so much so that for accelerations between 0.2 to 0.3 g, you cannot find a viable design solution. So at one point you have to say, no, I cannot build this wall with a steel sheet pile. Of course, you get much more economic solutions if you use finite element of finite differences, but as we said, this is very complicated analysis, and still there isn't an overall expertise to do this. So the question that we asked ourselves a few years back when we started thinking about this system was, can we find an alternative and possibly performance-based design approach that is both simple and more rational? So we'll produce a design that is doable, but it doesn't require really complex numerical analysis. Now, of course, in the area of the performance-based seismic design, the main requirement is that the demand, the seismic demand, should be less than the seismic capacity. And of course, both the demand and the capacity depend on the limit state that you are considering. For instance, if you are considering as a visibility limit state, you want to limit the deformations of your system under frequent and therefore weaker earthquakes. And so the sort of things you want to look at in your system are, of course, the strength, but also the stiffness of the structural elements will play a significant role. If you're looking at the ultimate limit state, you want to avoid the brittle failure of your structure. And this is, of course, under a rarer but significantly stronger earthquake. And so the sort of components, properties of your system that you want to look at are the strength, of course, but also the ductility. How much can the system accommodate for large displacements without failing? And so we are faced with the thing that we need to define, find a candidate to define the seismic capacity of the system, and also we need to be able to evaluate the performance, that is the seismic demand. And this performance can be in terms of displacements, so what are the residual permanent displacements at the end of the strong motion, and this would go under the hat of the geotechnical design, or what is the capacity to demand ratio for the structural elements, and this would go a little more under the structural design type of aspect. Okay. So if we go for a displacement-based approach, we might think of computing the displacement of the structure and comparing them directly with some admissible value of the displacement. Or, which is much more common in our type of codes of regulation, you go for a force-based approach in which you require that the maximum acceleration expected at the sites is less than some critical value of the acceleration, that is the acceleration that fully mobilizes the strength of the system. You might have noticed that there is this beta in front of a max. This beta is exactly a ductility coefficient, which is typically less than 1, so you don't take directly the maximum acceleration, you get a reduced value of the design acceleration, and this beta is a function of the admissible displacement. So you evaluate what sort of beta can you use, by how much you can reduce the maximum acceleration, taking into account the ductility of your system. So it is clear that the displacements are very, very important. Now, when we look at the performance-based design of gravity or semi-gravity retained wall, the type of approach that is used more often to look at the displacements is the Newmark's method. So in Newmark's method, the system that Newmark analyzed is a rigid block with weight, so the weight of the block is W, which is resting on some frictional base, and then the base is accelerated using some time history. Now, if the acceleration is less than the critical acceleration of the system, which in this case is the acceleration that is required to fully mobilize the frictional strength at the base of the block, of course there are no relative displacements between the block and the base. The absolute acceleration of the block is equal to the acceleration of the base, and the internal force, that is the force at the contact between the block and the base, is directly proportional to the acceleration. On the other hand, if the acceleration is larger than the critical acceleration, in this case you have non-zero relative displacements, the block will slide relative to the base, but the absolute acceleration of the block would be limited to the critical acceleration, and the internal force would be limited to the strength of the system. So they are both constant and equal to the value that they have when the base acceleration is equal to the critical acceleration. And during the sliding, you can work out the relative displacements, the permanent displacements of the block and the base by double integration of the relative acceleration over the time intervals in which the relative velocity is non-zero. So this is more or less very quickly what we do to work out with some little changes. There is this eta factor that is essentially something very close to 1, but to take into account the geometry. A retaining wall, a gravity retaining wall, is not exactly a block resting on a horizontal plane. Now, can this approach be also applied for flexible, anchored retaining structures? The problem is that we want to move from this very, very simple system to something which is much more complicated. Here I have put a little cartoon of what the system consisting of the main wall, the anchor wall, and some wedge of soil moving with the wall might look like. So yes, we can try, but we have some fundamental questions. The first one, how do we compute the critical acceleration? To what failure mechanism would this critical acceleration correspond? For the block, it's super easy. The block doesn't have anything else to do than slide backwards and forward. For a wall, this might involve some complex kinematics, some deformability of the system. We will have to think about it. What about the maximum internal forces? By internal forces, I mean the anchor force and the maximum bending moment in the wall. Are they really bounded by their critical values as the limiting strength at the base of the block? And third, how can we compute the permanent displacements of this block? Is the rigid block assumption something we can use? So with these three questions in mind, we can look at what we can do for these systems. First of all, we need to identify the plastic mechanisms, and with the rationale of the strength hierarchy, these systems are typically designed in such a way to exclude the rupture of the tendon, of the tie back, because this would be a brittle failure, not ductile failure. They are designed in such a way as to avoid yielding of the wall, so the formation of plastic hinges in the wall, both the main wall and the anchor wall, typical because they would be very difficult to repair. And so any plastic mechanism must involve the soil surrounding the structure. And also, for the sake of this lecture, because we don't have a lot of time, I will just consider a dry system, so I will throw out of the window all complications that have to do with the water, both in the backfill and in front of the wall. Now, what sort of mechanisms can we think of? Of course, the wall might fail by toe failure. That is, the passive strength in front of the toe of the wall is reached, and the bottom of the wall moves outwards. Or the wall might fail by anchor failure. So in this case, it is the passive strength of the soil in front of the anchor that is reached, and the anchor fails. And again, in this case, the wall rotates, but again outwards, but around the point that is towards its base. And both these mechanisms, we call them as local failures, because they correspond to local failures of the soil in critical parts around the structure. Or you might imagine that this wall is failing with a global failure, so there is an entire wedge of soil that is contained between the surface, the main wall, the anchor wall, and some sliding surface that is moving about as the soil is failing. Now, over the years, and the question is, which one of these three mechanisms is going to be critical? Now, over the years, we have developed a number of limit equilibrium pseudostatic solutions in which essentially we assume an earth pressure distribution around the wall and can compute the critical acceleration that correspond to toe failure, anchor failure, and global failure. And we can define the critical mechanism as the mechanism for which the critical coefficient is the smallest. So the critical mechanism is the one that has the minimum value of the critical seismic coefficient. And of course, with these same methods, you can also work out what the internal forces are, what the anchor force and the bending moment in the wall are at failure. So we have an operating definition of the critical acceleration for these systems. Now, these theoretical solutions, so limit equilibrium solution, were also verified by numerical analysis. In this case, we used plane strain numerical analysis using the finite difference code FLAC. And the soil was modeled as elastic perfectly plastic with more Coulomb yield criterion and non-associated flow with zero dilatancy, and the non-linear hysteretic behavior of the soil within the yield surface was reproduced by this sigma 3, that is a model available in the library of Flack, with Masing rules to simulate cycling, loading and unloading cycles. All the structural elements, such as beam and cables, were linear elastic, and there were elastoplastic interfaces at the contact between the soil and the ground. With these numerical models, we ran two types of analysis: pseudostatic pushover analysis, in which the horizontal acceleration was increased until we couldn't find anymore a numerical solution, and full dynamic analysis, which were carried out with periodic boundaries and real acceleration time histories, so a variety of real acceleration time histories that were imposed at the base of the model. And with this analysis, both pseudostatic and full dynamic analysis, we examined a variety of different layouts, changing the length of the tendon, the position in which it was anchored, and the depth of embedment, and so on. Now, of all this analysis, I just want to look at two, case A and case B. One of them corresponded to anchor failure, and another one corresponded to global failure, because the layout of the retaining structure will affect which mechanism is critical for the system. So we will concentrate on one of the walls in group A and one of the walls in group B, and I'm simply using this one because the layout is exactly the same, but for the point at which the tendon is anchored on the main wall. So they're very, very similar cases. And you can see this is the results from the numerical analysis. So this is the pushover analysis, where you can, immediately before, you cannot find convergence anymore, and so you can define the numerical critical coefficient and the critical coefficient found by limit equilibrium. And you can see that both for anchor failure and for global failure, there is a very, very good agreement between the numerical values of the critical coefficient obtained by pushover analysis and the ones that we obtained by limit equilibrium, which is kind of reassuring. And also, we can look at the internal forces. So these are normalized to be able to compare different layouts, but essentially this is the maximum bending moment in the wall as a function of the seismic coefficient, and the anchor force as a function on the anchor coefficient. And what we are comparing is the limit equilibrium versus the numerical pseudostatic analysis. And you can see that once the horizontal acceleration is larger than the critical acceleration, the maximum internal forces don't increase anymore. So there is a limit. And so once you hover the critical acceleration, the internal forces are bound by their critical value. In this slide, I've also included the results of the numerical dynamic analysis, which essentially are confirming the same thing. So you can use the critical acceleration for the structural design of your system, because even if the acceleration exceeds the critical acceleration, the internal forces in the wall will not increase above their critical values. This is true for a local failure of the anchor. Is this the case also for a global failure? So B was global failure. And in this case, you can see that no, both the pseudostatic pushover analysis and the dynamic analysis are telling us that the forces, the internal forces, can be higher than the value computed using the critical coefficient that corresponds to global failure. But if you then use the smallest of the two local failure coefficients, again, you are bounding the forces. So for global failure and the structural design, you have to use the smallest of the two critical coefficients corresponding to local failure, not the critical coefficient corresponding to global failure. Finally, some words on displacements. These are all the displacements that they are computed from the numerical analysis, the full numerical analysis for local mechanisms in red and global mechanisms in blue. And they're plotted in a plot of the ratio A critical over A max as a function of the observed displacement in a logarithmic scale. Now, you might notice that for A critical over A max greater than 1, which means when the maximum acceleration is less than the critical acceleration, so the strength of the system is not yet fully mobilized, the displacements are non-zero. So there are displacements even before you reach full mobilization of the strength. And if you look at the indication, the ductility as a function, ductility factor beta as a function of displacement, which is included in NTC 2018, this is not the case, because the NTC, this ductility factor was derived using Newmark's block analysis and not proper calculation of displacement. So you might use better ductility functions, and this is a proposal. It's a proposal that is contained in an article that I submitted with Riccardo Conti to Soil Dynamics and Earthquake Engineering. But more importantly, you have to consider that this system is not a rigid block resting on a rigid base. So in that case, the system is rigid, perfectly plastic. There are no displacement before failure, whereas a wall will accumulate displacement. So there is a non-linear initial phase in which displacements are accumulated before the critical acceleration is reached, and then you get to the critical state. Now, there are a lot of simplified dynamic methods that are really quite simple to use. The nonlinear single degree of freedom method proposed by Callisto, the generalized Newmark method that I contributed to with other people, the dynamic limit equilibrium by Giorgio Caputo. Essentially, they all share this factor, that is the nonlinearity before failure is accounted for by a pushover curve. And I don't have the time to go into the details, but I just want to show you that if you compare the displacement that you get from single degree of freedom, generalized Newmark method, or dynamic limit equilibrium method with the numerical displacements, these are very close to one another. So we can predict displacements with very simple methods that do not require putting together a very complicated dynamic, fully dynamic analysis. All you need is a pushover analysis, which is a static analysis. And of course, the agreement is even better if you remain in the displacements that are of the order of half a meter. That is reasonable. So to conclude, I hope that I've convinced you that the critical acceleration is a crucial ingredient. In fact, this is the capacity of the system. This is the strength of the system. And it can be used both for the structural design, so to define the maximum internal forces, and the geotechnical design, the displacements. That pseudostatic limit equilibrium methods can be used to identify the failure mechanisms and the critical acceleration, and also to compute the maximum internal forces in the system. That the maximum internal forces are bound by critical values, not always those corresponding to the actual failure mechanism, but some other one, and that the activation of a ductile plastic mechanism is inherently safe because the structural elements are protected. They will not experience any bigger forces. And for permanent displacements, the rigid block assumptions is not applicable. There are other simple methods that can take into account the nonlinear behavior and the complex kinematics of this system. And I'm done. I hope I haven't overrun too much. Okay.
Thank you Giulia, grazie. Chiedo se ci sono delle osservazioni o delle domande. Maybe one curiosity for me, thank you for your interesting presentation. You know that one of the missions of ReLUIS is also to contribute to the new code in Italy. I was wondering if all this approach, if you know how this approach is related to our norme tecniche per le costruzioni.
I know that some of this is under review. There is a lot of discussion about what you should consider a ductile retaining structure. So because some of them are very obvious, like the gravity and semi-gravity retaining walls, this is less obvious for embedded flexible walls. So for instance, Luigi Callisto and I have had many very pugnacious conversations around how to modify the codes. And it's not just for the norme tecniche, it's also for the new version of Eurocode. So there is debate around this, and I truly hope that this can be included in the new regulation, because it is a much more rational way of designing. And I think that if you keep in mind this idea of the hierarchy of strength, which in reality we have mutuated from the structural community. So we didn't really think in this way only, say, 10 or 15 years back. So it's taken some positive interaction with the structural community to think in terms of hierarchy of strengths and then ductile system, and including ductility. You don't need to include ductility explicit in the calculations you do. It's in beta, so beta needs to be a function of your admissible deformation, but then you need to have a beta versus u relationship which is realistic. You can't go on with the direct application of Newmark's block because that's wrong. And note that beta might even be larger than 1 if your admissible displacements are really small, which is unheard of. A ductility coefficients that can be larger than 1, but this is what the results are saying. So, if I may add, I had to, because we didn't have a lot of time, so I cut out an entire chunk of this presentation that was a little bit to do with water and a little bit to do with physical modeling. So I was super happy that the previous presentation had a lot around testing, because we do a lot of reduced scale modeling in a geotechnical centrifuge of geotechnical systems. And I was super happy that there was an element of experimental work, because this is super important. And all our experimental work is confirming the results we get by theoretical and numerical analysis.
Thank you, Giulia. I think this presentation is perfectly in line with the ReLUIS activities, because you are trying to give a support to practitioners, because you said that. And also, I remember one of your first slides where you showed that the cost become very high if you use less advanced methods. So coming back to what Rui and others yesterday were saying, one of our mission is also to share with the professionals. You are saying, I'm not considering directly the activity, but is in a coefficient. This is, I think, the contribution of science to translate all these in tools, practical tools. And so I'm also hope that this approach can be included in the review, also in the Italian code. Thank you very much.
Thank you, Andrea.
Ringraziamo allora i nostri due colleghi.